This is the notes for section 8.5, products with radicals. And what we want to do is, from a big idea standpoint here, is that we want to be able to think about the product of nth root of non-negative numbers. Key non-negative is the nth root of the product of the numbers. So let's see if we can figure out what that really means. So if you think back to earlier lessons, one thing that we learned was that if I have the square root of a times the square root of b, that's just equal to the square root of a times b, as long as those existed. So in other words, if I have the square root of 2 times the square root of 8, that's equal to the square root of 16, which can be helpful because we can find the square root of 16 very easily, and we know that that's equal to 4. Okay, well, we're going to take that idea and extend that now to not just square roots, but really any roots, as long as we're talking about non-negative real numbers and n being greater than or equal to 2. And we call this the root of a product theorem. Okay, now we can apply it both with fractional or rational exponents as well as radical form. So let's take a look at this example down here. It says calculate the third root of 320 times the third root of 25. Well, if I were to do the third root of 320 or the third root of 25, neither of them are nice, neat third roots. However, if I multiply those together, if I take 320 and I multiply it by 25, now kind of how you want to do that in your head, you should be able to figure out that that's equal to 8,000. So really I'm saying, well, what is the third root of 8,000 going to be equal to? Well, the third root of 8,000, what number can I multiply by itself 3 times and get 8,000? Well, I know that 2 times itself 3 times is equal to 8. So if I take 20 times itself 3 times, I should get 8,000, which I do. So really this is equal to 20. Alright, so let's take a look at the second example, which is a level 1 type question. And first of all, we have to assume that x is greater than or equal to 0. So what we want to do is we want to perform our multiplication here and simplify. So if I have the fifth root of 8x squared and the fifth root of 4x to the eighth, I'm going to combine that into 1. So really I'm saying the fifth root of 8 times 4 times x squared times x to the eighth. Now, since it's all multiplication, it doesn't matter which order I do things in or which order I multiply things in. So if I think about 8 times 4, that's equal to 32. So really I'm looking at the fifth root of 32. And then if I have x to the second and x to the eighth, I can use my powers here and add them together and get x to the 10th. Alright, so let's see if we can simplify that any further. I'm going to go to the next thing I'm going to do is I'm going to say, alright, well 32, I know the fifth root of 32, I know that 2 times itself 5 times is equal to 32, so that's going to be equal to 2. And then if I think about the fifth root of x to the 10th, that's really like saying 10 over 5. In other words, I'm saying, well, 5 divided by 10, well, I know it goes in there exactly 2 times, so I can actually simplify that to 2x squared. So the answer is 2x squared. So this whole thing simplified all the way is equal to 2x squared. Now that's something that you're going to have to be able to do from a level 1 standpoint in this chapter. Alright, so let's take a little closer look at how we can simplify radicals. So in general, to simplify an nth root, rewrite the expression under the radical sign as the product of perfect nth powers and other factors. Then apply the root of product theorem. So let's look at what that means and how we can go about doing that. So if I look at this example, if I assume that both a and b are greater than or equal to 0, I want to pull everything out of the radical that I can. So in other words, in simplifying radicals, sometimes our simplified radical doesn't look any simpler than it started. We just need to pull everything out of the radical that we can. So what I'm going to do is I'm going to look at this and I'm going to do each number and each variable. So the first thing I'm going to do is I'm looking at the number 125, and I'm asking myself this question: is there any perfect third power numbers that go into 125? And I know that 125 is a perfect third power number. So what I'm going to do is I'm going to say, okay, since 5 times itself 3 times is equal to 125, I can pull the 5 out of the radical. I don't have anything left underneath the radical, so I'm done with the number. The next thing I'm going to do is I'm going to look at the variables, and I have a to the 12th. And I'm really saying, well, how many third a's are there? So in other words, I'm going to take 12 and I'm going to divide it by 3. So we're going to take the power and divide it by the root, just like we know power on top, root on bottom. So it's really like saying a to the 12 over 3. And b to the 27 over 3. Now, here's the deal, though. We want to write this in radical notation. So if it doesn't go in there nicely, then we have to do something different about that. Okay? So we have 12 over 3. Well, 3 goes into 12 evenly 4 times, so I can actually pull all my a's out, and I have 5a to the 4th. And I notice that 3 goes evenly into 27 as well, so I would have b to the 9th. Therefore, I was able to pull everything out of a radical, and this is my simplified answer. Okay? All right, so let's take a look at this third example. In the example above was kind of an easier example because every single thing that was underneath the radical was a perfect third power number. So I didn't end up with anything left underneath the radical there. So I was able to get everything out of the radical. On this one, that's not going to be the case. So let's see if we can simplify this right here. We want to write this with a smaller power of y inside the radical. In other words, I want to pull everything out of the radical that I can. So what I'm going to do is I'm going to think about this kind of as two separate problems, and then I'm going to put them together. So I'm going to think about the fifth root of 96, and I'm also going to think about the fifth root of y to the 11th. So let's start with that number. Now, 96 is not a perfect fifth power number. So what I have to do is I have to ask myself this question: are there any perfect fifth power numbers that evenly divide into 96? And it turns out there is. If I take 32, which is a perfect fifth power number, and I multiply it by 3, that's equal to 96. So this is the same as this. Oops, I'm sorry, there should be a fifth power there. Now, I know the fifth power of 32 is equal to 2. So what I can do is I can pull that 2 outside my radical and leave the 3 underneath the radical. Okay? So I've now simplified the number part. Now let's see if we can simplify the variable part. Well, that's actually a little bit easier. The variable part, what I do is I say, okay, I think of it kind of as a fraction. So I think about that as being like a y to the 11 fifths. Well, I know that 5 goes into 11 evenly 2 times. So really what that means is that I can pull 2 y's out of the radical. So I can say y squared is outside the radical. Now whatever is left over, kind of the remainder, if you think about when you first learned how to divide, that remainder is how many y's are going to stay in the radical. So in other words, since there's 1 left over when I take 5 times 2 and I get 10, there's going to be 1 y that's going to remain underneath the radical. So I have 2 times the fifth root of 3, and y squared times the fifth root of y. Now I want to take this, and I want to put them back together. So I'm going to have outside the radical 2y squared. But inside the radical, I still have 3y y. And although it doesn't look any more simplified because I've pulled everything out of the radical that I can, this is the simplified version of this. So this is the answer we would be looking for.